Okay, let's get started. Okay, can anybody tell me what we are doing right now? Ben, how about you? You have the boldness to look in this direction. Yes. Go ahead.
Linear transformations.
Linear transformations, yes, that's sort of the broad topic. Now, what are we doing about linear transformations?
Different bases with respect to different systems.
Okay, so you need to say, you're missing one word, Avery?
We're creating matrices that represent those linear transformations.
Represent, yeah, so representation. So we're creating, you have some, right, you have some linear transformation going from one vector space to another vector space, right? And we've been creating, the main idea for the last several days has been, how do you make a matrix that somehow represents everything there is to know about the linear transformation, right? And sort of our ultimate result is that if you have a basis E, let's call this Vi from I equals 1 to n, and you have another basis F being, say, Wi from I equals 1 to m, say, then it's possible, right? So if you have these bases, then you have the coordinate vector maps, right? We have the coordinate vector maps P and Q, right? So where P of V is the coordinate vector with respect to the E basis, Q of W is the coordinate vector of W with respect to the F basis, right? So you've got these two. Once you have the bases, right? Once you have the bases, then you have the coordinate vector map, right? And our ultimate result is that you can get a matrix. You can get a matrix to go from here to here, right? In such a way that this diagram commutes, right? In such a way that that going this way or this way ends up with the same result, right? Okay, right? Okay. What was that matrix? What was that A? Does anybody remember how you construct that A? How do you construct that A? How do you construct that A? Anybody remember? You are looking down. Turn to somebody nearby and say, I think it was something like this. It was like this. Turn to somebody nearby and tell them what you remember about constructing the A.
It was just yesterday. Yeah, I know. I looked at this one last night and started thinking it was like something and then the Euclidean columns.
Yeah,
it was.
Because when we did the rotation.
Okay. Anybody remember? How do you construct the A? Anybody remember? Anybody remember? Lizzie, you look like you may or may not remember.
Okay.
Yes.
It's A of VE, like V with respect to E.
So this is what the matrix will do, right?
Yeah.
This is what the matrix will do. A of VE will be
T of V.
TV with respect to the F basis, right? So that's what the matrix will do once we make it. But how do you make it? Does anybody remember? Nico?
I remember when we had the actual pieces that were in the two different places we were trying to get to, and then we would write. I think we would perform the transformation on one of them, and then we would say, okay, how would I write this in column vector form in terms of the other side?
Exactly. Yeah. So that's you. I don't know if you remember it exactly, but you've certainly got a lot of it right there. So the columns of A you get by transforming each of the basis elements. Transforming each of the basis elements of V, and then taking their coordinate vectors with respect to the W basis. Right? You take your basis over here, you map it over here, you put it into the coordinate vectors, and use those coordinate vectors as your columns, and that's the matrix you're looking for. Okay. This is just to remind you what's going on. Okay. There's another way of thinking about it. Okay, so if you forget, there's another way to remember. Maybe one way to remember is this. Okay, so remember at the very beginning. Remember at the very beginning when we were going from Rn to Rm, right? If we had a linear transformation going from Rn to Rm, right? Let me call this big guy L, so I don't get confused with the T over there. Okay. We were able to get some matrix A. I'm going to call it A naught. Okay. We were able to get a matrix A naught so that we could get A naught such that T sub A naught actually was L. Right? If you left multiplied by that A naught, that was L. Do you remember that? That's the first kind of matrix representation we did. Right? If we're going from Rn to Rm. Right? And the way we got that matrix was by does anybody remember? Anybody remember? The way we got that was by taking the standard basis elements and mapping them over here, right? We took the standard basis where recall A naught was, all you did was you took the standard basis elements, this should be L's, LE1, LE2, LEN. Right? Do you remember that? I hope you remember that. We had some example like L of x1, x2, x3 was x1, x1 plus x2, x1 plus x2 plus x3, right? And we saw that the way you got the corresponding matrix was it was going to be 1, 1, 1, 0, 1, 1, 0, 0, 1. Okay. Everybody remember that? That's the first. This is like the first example that we did. Okay. Okay. Right. So the way you got it was by mapping over the standard basis elements over through the linear transformation. Right? Right. That was like the most simple kind of matrix representation. Okay. Okay. So I want to do, let's do that. Do that with, let's do that with this thing here. Okay. Okay, so everybody look. Our linear transformation goes from V to W, right? It doesn't go from Rn to Rm. So what am I talking about, right? Am I just saying nonsense here? We're not going to look at that. What we're going to look at is this. Okay, we're going to look at this map. Remember, these guys can go backwards, right? These guys are invertible, right? So what we're going to do is look at, consider P inverse followed by T followed by Q. Okay, P inverse followed by T followed by Q. Okay. that goes from Rn to Rm. Okay. What is A naught for this map? What is A naught for this map? Right? This is a map from Rn to Rm. This is a map from Rn to Rm. So, you know, just like this map from R3 to R3, it's going to have some matrix representation. Right? And the way you get that matrix representation is by looking at how it acts on the standard basis. Okay? So what happens to the standard basis when you go through this? I'll let you think about it for 1 minute or two. Think about it for 2 minutes, and if somebody figures it out, I'll give you 3 points on the exam. No, 4 points on the exam. I'm going to wander around outside. Who thinks they have an idea? Okay, talk to each other for a bit. Talk to each other for a bit, and then I'll ask you what you think.
But I mean, this is representative. This is slightly different. Yeah. So, we already have the answer.
Okay, so you know we're still going to have the E and F, right? This P and Q come from the E and F, as over there, right? So E comes from some basis, F comes from some other basis. Okay. Who wants to talk? The people who have their hands up don't have them up anymore. Read.
Okay, we thought that it was the A naught matrix for this transformation is just what we have written up over there. It's just the matrix made up of the columns of the transformation applied to the first basis onto.
Okay, so that's sort of clear, right? Because just like games are shifting, we know that's what we're going to get. So explain it to me. Why is that? Why does that happen?
So in the first one, we applied the.
Yeah. So let's think. What happens? You want you apply this thing to these basis elements. Right?
Yeah.
And what do you get?
So in our super simple example, our basis elements were just E1, E2 through En, and we just applied it to all of them. So we're applying these to our basis elements. So P inverse.
Yeah, what's P inverse of E1? Or E, let's try just E1. Okay, what's P inverse of E1?
P inverse of E1 takes us from our, it takes us from Rn to V, and
so what is P inverse of E1? So we're going to have, if you have to understand this in pieces, so this will be P inverse of E1. Well, what's P inverse of E1?
B, right?
V is the whole
V1.
space. V1. Yeah, so this will actually be V1. V1, right?
And
And then W1.
So then you get T of V1 hit with Q. Well, what's T of V1 hit with Q?
W.
Yeah.
It's not W1, but
Or
it is
T of V1 is W1.
T of V1 with respect to the W basis is what it is.
Oh,
T of V1 with respect to the W basis,
okay.
right? Because what does Q do? It takes something and gives you the coordinate vector of it with respect to the W basis, with respect to the F basis, excuse me, right? The basis for W.
And then don't you know what A is?
Right, and so then, right, so that's the first column of your matrix representation, right? And if we take E2, if we take EI, we just put in i's here. We just put these dots in, right? So what you see is that the matrix representation for QTP inverse is the matrix representation of T with respect to E and F. So maybe it's clear if I read it like this. The matrix representation of QTP inverse from Rn to Rm is the matrix representation of T from V to W with respect to E and F. I'll give you guys 2 points for that.
We tried.
You're close. You were close.
Consolation.
Consolation prize. Yeah. It's not a bad one. Yeah. Okay. Okay. So, are people getting it? People getting it? Right? Right? Here's this thing, right? The matrix representation of T with respect to E and F. Right? The way you construct it is like this. Okay. Or if you forget, you think about this guy, right? And the matrix representation of this guy from here to here is the same thing. It's exactly the same thing. Okay. Any questions? Read. Yes.
Wait. So for each EI we get that, and
Yeah.
so when you add all those up, you add them as columns into
You
one?
put them as
Okay.
columns. You use them as columns of your matrix representation.
Okay, and that's
Right.
because, when you multiply, they'll be applied to
Yeah.
the thing?
Right.
Okay.
Remember this example.
Yes.
Yeah. Okay. Yeah. Stella.
I have questions.
Yeah.
Why P minus 1 EI equals to VI?
Why is P inverse of EI VI? Well, what does P do? P takes a vector and then says, it gives you the coordinate vector with respect to the E basis, right? Okay, so suppose your VE is 1, 0, 0, 0, 0, 0, right? What does that say about your vector? Remember how you get the coordinate vector? You express V as a combination, C1 of V1 plus Cn of Dn, and then you use these guys as your coordinate vector, C1 through Dn. If your C1 through Cn are 1, 0, 0, 0, 0, 0,
It's VI.
then your V must have been just Vi, right?
Okay, got it.
Okay. Yeah. Right. Your V was 1 of this guy plus 0 of everybody else. Well, then it's V1, right? Okay. So, okay. Oops, let me not use that, because that's what we need. Okay, so now let's go back to what we were talking about at the very end last time. Okay. So what we were talking about at the very end last time was switching bases, right? So recall what we had last time was suppose we have T going from Rn to Rm, right? And we have E, a basis of Rn, and F basis of Rm, right? Then so we've got Rn, Rm, right? So this is actually a simpler version of what we were doing before. Okay, so it's like, right, instead of going from V to W, we're going from Rn to Rm. Not some abstract vector spaces, but actually concrete, good old Euclidean spaces. Okay. Well, we still have, right, coordinate vector maps. Right? We still have coordinate vector maps, right, corresponding to E and F. Right? You have some vector here. P of V is the vector with respect to the E basis. Right? Q of W is W with respect to the L basis. Okay. But these are easier now. These coordinate maps are easier now. Like, does anybody remember? Well, I'm just going to tell you. Do you remember how do you get the coordinate vectors? You take the basis, use those guys as columns, invert it, and then multiply V by it, not multiply V by it. Right? Right, over here, this is going to be, you take your vector and you multiply it by the inverse of the W matrix. Okay, so then the matrix representation of T with respect to E and F is just A1 through AN, where the ith column is just going to be TVI hit with the inverse W matrix. Okay, that should be obvious. I hope that's obvious. Maybe it's not obvious, but it should be obvious. Okay, so everybody look for a second. Stop copying or copy faster. You guys need to write faster. Write faster. Okay, you know what the columns are going to be, right? The columns are going to be this, right? Okay, so the column going to be TVI with respect to the F basis, right? Well, you know what that is, right? That's TVI with W1 through WM inverse. Did I write the wrong thing before? Maybe I wrote the wrong. No?
I was too slow at copying, so I started watching.
Okay, I hope I wrote this before. Maybe that's why it wasn't
Yeah, you
obvious.
heard it before.
Okay, good. Thank God. I have no memory. Okay. Right. Well, this thing here is this guy with respect to the F basis. Well, that's just you multiply by the F basis is the inverse of the F basis matrix, right? And that gives you each of the columns. Okay. So this is just one instance of the more general thing here, right? In the case, so this is like in the case D is Rn and W is Rn. In the simple case, simpler. Okay, so let me make you do an exercise. Do an exercise. This is actually 18A from your book. We have a linear transformation. Tx is x3, x1. So it's a map from R3 to R2. Okay, a map from R3 to R2. Right. It takes x1, x2, x3, right, and it changes it to x3, x1. Okay. Take 10 seconds and tell me what the A naught is. What's the matrix representation just from R3 to R2? Remember how you get it? Just take the standard basis elements and map them over. Right? So what is it? Well, 1, 0, 0 turns into 0, 1, right? 0, 1, 0 turns into 0, 0. 0, 0, 1 turns into 1, 0. Okay? So that's the sort of like the direct representation of it. That's actually, this is the matrix representation of T with respect to the standard basis on both sides. Right? We kind of hit it. We just call this the matrix representation of T, but what it really is the matrix representation with respect to the standard basis. Okay. But I don't want that. I want you to use these guys. So E is going to be U1 is 1, 0, negative 1. U2 is 1, 2, 1. And U3 is negative 1, 1, 1. Okay. And then F, on the other side, is going to be B1 being 1, negative 1, and B2 being 2, negative 1. Okay. I want you to give me the matrix representation of T with respect to E and F. Okay. So just follow what we have over here on the right-hand side. Okay. So take 2 minutes and start calculating what that is. Just to make the theory more concrete for you. you don't have to go through with it. I just want to make sure you know how to do it. So set up how you would, make sure you know how you would do it. Okay, talk with somebody nearby. Okay, so how do we get it? How do we get it? Somebody want to tell me? Julia, you're talking a lot.
So just
Exhibit.
looking at AI, so the first thing we have is T, VI in
Yeah.
terms of F.
Exactly.
So you start with T, VI,
Yeah, so we need to take T of
or V1.
T of these
Or
guys.
V1.
Oops. T of U3, right? And when we do that, we're going to get x3, x1, so that's going to be -1, 1, 1, 1, and 1, -1. Right? Those are, you take your basis elements and you transform them over, and then what do you do?
So it's with respect to F, or like in the basis Fs.
Mhm.
So it would be -1, 1 equals something times 1, -1 plus something times 2, -1. And those coefficients are going to be the columns of A.
Exactly, exactly. So, yeah, so, and the way you get it is just by inverting the F matrix. So, so for each of these guys, right, A1 is going to be right, -1, 1 with respect to the F basis. Well, the way you get that is by inverting the B matrix, right? And that'll give you the coefficients that you just mentioned, right? Right. A2 is going to be the same thing: 1, -1, 2, -1, inverse of 1, 1, right? And A3 is going to be same thing, -1, 1, -1. Right? Okay. So, right, so, I mean, you could actually do this all in one move, right? So you just say, look, A is going to be this inverse times all three of these guys, -1, 1, 1, 1, 1, -1, right? You don't have to do them separately. You can do them all at the same time. Right. And it turns out to be -1, -3, 1, 0, 2, 0. The book points out that you could calculate this by taking 1, 2, negative 1, negative 1, negative 1, 1, 1, 1, 1, negative 1, and then doing row reduction on it, doing row reduction on the left thing to reduce it down to 1, 0, 0, 1, and at that time you're going to have, of course, the appropriate inverse. You'll have multiplied, because by doing this you're basically multiplying by the inverse. So you could do it that way. You could calculate by Gauss-Jordan reduction if you felt like it, or if you don't feel like it, just calculate the inverse by Gauss-Jordan and then multiply. Yeah, Nico.
I don't understand where you're getting the negative 1, 1, 1, and 1, and then negative 1, like 2.
These guys.
Yeah.
These guys, well, right, you need to take each of your basis elements and hit them with your linear transformation. Right? Right? The columns of your matrix representation.
Oh, it's upside, it makes it upside down. Okay. I got that it gets rid of the x2, but I was wondering why it was negative 1, 1 instead of 1.
Ah, yeah, it's x3, x1.
Okay, specifically has to do that.
Yeah, this is our example, right? This is our linear transformation, right? It takes x1, x2, x3 to x3, x1. So this is the guy we're trying to represent, right? If we had a different matrix, if we had a different linear transformation, it would do something different. Okay, but for this example, we have to see what it does to the basis elements here.
Okay, and then you multiply that by f inverse.
Basically, yeah, you take this thing, you put these guys into a matrix, take the inverse of it, and that will give you the coordinate vector with respect to the f basis. Right. So this thing here, what this thing is TU1 with respect to f. Right. You need to take T of your basis elements and then represent them with respect to the other basis. Okay. Any questions about that? Yeah, Nico, go ahead.
And why was, when we said the A naught, why was that 0, 0? Like, why is it a 2 by 3 instead of just like 1, 0, 1?
Well, what we're getting is a matrix that will allow us to go from R3 to R2. So it's got to be a 2 by 3, right? It has to be a 2 by 3 in order to go from, when you multiply a 3 by 1 by it, then you get a 2 by 1, right? So it's got to be a 2 by 3 matrix. And remember how you get it. You take each of the standard basis elements, and you use those guys as your columns, right? Well, T of 1, 0, 0 is 0, 1, right? 0, 1. T of 0, 1, 0 is 0, 0, right? X3, X1. T of 0, 0, 1 is X3, X1. Right, so you take each of those guys and you hit them with the linear transformation and see what you get. Okay. Okay. Actually, let me stop here. I'm going to take a poll. So I usually do this a little bit earlier, but we'll do it now. Better late than never.